Yeah, there we go. Mars 2020. So Mars, I decided to do a talk on astronomy because we haven't really had one in a while. And every 2 years and some odd, Mars sort of gets into the news. Fortunately, the stories that Mars is going to get as big as the full moon during these times has finally stopped. I haven't seen that anywhere, which is always kind of nice. So why does this happen? Why do astronomers get really interested in Mars, especially amateur astronomers, people like myself that enjoy looking at it? Well, it has to do with what are called oppositions. And an opposition is not the bunch of people that sit in the House of Commons whacking their hands on the bench and making weird noises. The opposition is an astronomical term. And what an opposition is something that happens with the Earth and planets that are called superior planets, or planets in what are called superior orbits. That's simply a fancy way of saying that the planet has an orbit bigger than the Earth. So here we have a little diagram that shows the sun. Nothing on here is to scale. We have the Earth moving around the sun, and this little arrow represents the fact that the Earth is moving along at a pretty good clip. And any superior planet, and as it turns out there are 5 of them, most diagrams tend to pick red as the one because most people assume you're talking about Mars. But these planets also move around the sun, but they don't move as quickly as the Earth does. And as it turns out, the farther out the planet is from the sun, the bigger the orbit it is and the slower it moves. So opposition is the point when the Earth is between the sun and the superior planet. So the sun is on one side of the Earth, the superior planet is on the opposite side of the Earth. So we get to see it at midnight, up nice and high in the sky. And why does this thing not want to? Oh, there we go. No, back up. Back up. I think I figured out the problem. I think it thinks I was in Zoom there for a second. Okay, so the 5 planets that are that have superior orbits to that of the Earth are going out from the Earth are Mars, then Jupiter, then Saturn, then Uranus, and then Neptune. And one of the things that comes up when it comes to opposition is how long it takes to go from one opposition to the next opposition. And the term that's used in astronomy for that is called a synodic period. It comes from the word synod, meaning a gathering together. Generally in modern day life, the only time you might come across the word synod is to do with something to do with the church. A gathering of cardinals, for example, in the Catholic Church is usually referred to as the synod. But the synodic period is how long it takes to go from one opposition to the next opposition. And this little animation is sort of going to show you how that works. Again, you'll notice that they pick red as the color for the superior planet because they assume you're talking about Mars. This applies to all 5 of the planets that have orbits bigger than that of the Earth. So I'm going to run the little animation, and what we have right now is one opposition. The Earth continues in its orbit. The superior planet moving slower and in a bigger orbit lags behind, and then the Earth catches up to it again. So you can see that by looking at this, it's fairly obvious that oppositions, the synodic period for an opposition is going to be more than a year for any of the or any of the planets that have superior orbits, because while the Earth is moving around, they are slowly but surely moving ahead of where they used to be, and the Earth has to go a little extra bit in order to catch up with them to have another opposition. Now, what this tends to do with the planets is it changes our view of them. So we take a look at this first image. So there's Neptune. Neptune takes 368 days. That's its synodic period. So basically, Neptune doesn't really move very much in the time it takes the Earth to go around its orbit once, the day being just over 365 days long. So oppositions of Neptune occur a few days later every single year. So if it happens on October 1st one year, it'll be like October 3rd or 4th the next year. So more or less very easy. You have one every year. If you then take a look at Uranus, 370 days. So really not much different because we're still in the outer part of the solar system where things have big orbits and move slowly. If we look at Saturn, even though we're coming in closer to the sun, still 378 days. So not that much more than a year. When you get down to Jupiter, we're up to almost 400 days. Now, there's 365 days in a year, so that's about a month longer. So oppositions of Jupiter occur about a month later each year. So if they occur in August one year, the next year they'll be in September, the next year they'll be in October, and so on. And then we come to Mars, which is actually has an orbit just outside the orbit of the Earth. So it has a small orbit, and it's also moving fairly quickly. So in the case of Mars, it takes 780 days for Mars to actually catch up, for us to catch up to it again. And that's over 2 years. I'm going to come back to that. Now, as the Earth moves around in its orbit, when it's at opposition, the Earth is here in the middle. There's our superior planet again. And that is as close as we're going to get to it. When the Earth is over here on the far side of its orbit, so let's say that we've just come around from the sun, and up it comes, like that. Okay. Earth is not as close. So as the Earth moves around in its orbit, the distance from the Earth to any superior planet is going to change over time. And what that tends to do is it means that the apparent size of the planet is going to change and the brightness of the planet is going to change. Well, let's take a look first at apparent size. And to get this right, I'm just going to go off for just a second, talk about angles in astronomy, because we tend to use angles in astronomy that you very rarely come across in every regular everyday life. We still have the same number, so there's still 360 degrees in a circle. But if you've ever used a protractor in school, here's a standard protractor, and it has little marks there that show you 1 degree intervals. In astronomy, we break those 1 degree intervals down into 60 smaller pieces called arc minutes. So in every single one of those little 1 degrees, imagine you put 60 little tiny marks. Each of those is 1 arc minute. It's a very small angle. Now, to give you a bit of an idea, the apparent angle of the moon, so if you go and look at the full moon, and I should point out, most first-year astronomy books tend to use a picture like this. This, by the way, is not a full moon. This is actually 2 quarter moons stuck together in Photoshop. And you can sort of see that because if you look on the left-hand side, you'll see that the shadows of all the craters are on the left side. And if you look at them over here, the shadows are all on the right side. But the really full moon is really blanded to look at. So I decided to use that one. It makes an angle of about ½ a degree. It's also the angle of an aspirin held up at arm's length. That's about ½ of a degree, or because there's 60 arc minutes in a degree, about 30 arc minutes. Now, each of those arc minutes is divided up into 60 even smaller little angles called arc seconds. So there's 60 arc seconds in 1 arc minute. So how big is 1 arc second? Well, the angle something makes depends on its size, but it also depends on its distance from you. So if you take a $2 coin and say to yourself, how far away do I have to move that $2 coin until the angle from one side to the other is only 1 arc second? It turns out that's 5 kilometers away. You'd be lucky to even see the coin, let alone be able to see the angle from one side to another. And with modern technology, astronomers can actually measure angles of micro arc seconds. That's millionths of an arc second. So the technology for measuring angles has gotten really, really good. So let's take a look at how this, now that we know how astronomers measure angles, let's go back to this idea of the apparent size of planets and the brightness of planets. And we'll go back, start with apparent size. So we're going to again work our way inwards from the outermost planet. So here's Neptune. So Neptune, when it's at the farthest part of its orbit, when we're just coming around from the sun, it has an apparent size of only 2.1 arc seconds. So imagine taking 2 $2 coins side by side at 5 kilometers. That's how big it appears in the sky. Very small angle. And you'll see that even when it's at the closest, when it's at opposition, it barely gets any bigger because it's so far away that us being on one side of the sun or the other side of the sun doesn't really have any great impact one way or the other. Come into Uranus, you notice that Uranus is noticeably bigger than Neptune. They're both the same physical size, but because Uranus is closer, it looks bigger in the sky. But again, there's not that much difference between it when it's at its farthest point from the Earth and its biggest point, but you can actually sort of see a bit of a difference. Okay, back in here. Saturn's quite a bit bigger, and now you can start to see that because we're getting into the inner part of the solar system, Saturn gets noticeably bigger between when it's farthest from the Earth and when it's closest to the Earth. This is Jupiter, and these planets are all scaled at the actual same relative size. You can see how big one of them appears at a telescope compared to the others. Jupiter is the biggest because it's the largest planet, and it's definitely closest to us. But you'll notice that even Jupiter doesn't even get twice as big from the time when it's smallest to the time when it's biggest. But look at what happens to Mars. Mars goes from almost the same size as Uranus to almost as big as Jupiter when Jupiter's at the far point in its orbit from us. So it gets roughly 7 times bigger over this period of time, which is why astronomers really look forward towards oppositions of Mars, because it gets really, really big and you can see lots and lots of detail on it. And this is what Mars would actually look like through a fixed magnification telescope from March of this year to March of next year. And as you can see, we're almost here. And you can see how big Mars gets right around that time of opposition. It gets really, really huge in the sky. Now, it also gets a lot brighter. Now, this diagram is from the Observer's Handbook. And don't worry about this magnitude system on the left-hand side. Astronomers years ago, like back in ancient Greek time, came up with a way of measuring brightness by saying, we'll call the brightest stars. Oh, maybe that's what this thing means. Let me just pop out here. Just had 2 other people that joined us. So astronomers came with this system where they said, okay, we're going to classify the stars. We'll make the brightest ones, we'll call them first magnitude. The next brightest we'll call second, and then third, and then fourth, and then fifth, and then sixth. And they lumped together a lot of really bright stars in this category of first magnitude. And then as it became possible to measure the light coming from stars, they realized that some of those first magnitude stars were much, much brighter than other ones. So something that's brighter than a first magnitude, because they picked the system with it getting fainter as the number got bigger, you have 0 magnitude is even brighter than a first magnitude star, and then it goes -1, -2, -3, -4. Drives people nuts until you get used to it. But you can see what's plotted here. This is, again, this is from the Observer's Handbook. This is from the 2020 edition. And you can see the brightness of Jupiter. Jupiter had opposition in the middle of July. But remember, Jupiter doesn't get that much bigger. So it doesn't get that much brighter, but it's definitely brighter at opposition than it was when it was further away. And you see if I can, yeah, oh, that's what the program's been doing. It's been kicking me back to Zoom every time somebody wants to join. Okay, but no, go back one. Same thing with Saturn. So here's Saturn. Saturn had opposition just after Jupiter this year. And again, you'll notice it's quite a bit fainter than Jupiter is because it's further away and it doesn't get as big. And then look at Mars. Mars just comes out of nowhere, gets almost as bright as Jupiter is, and then it quickly fades again. So I'm going to show you how to find Mars by yourself. You'll have no trouble finding it. It is really, really bright. Now, if you go back to this idea of Mars's synodic period, remember I mentioned that it's 780 days. And if you work that out in terms of years, it's 2 years plus about 50 days. So oppositions of Mars don't come every year. They come every 2 years and almost 2 months. And what that means is that because they don't come very often, that's one of the reasons astronomers get excited about them. Now, this is a diagram that's, as you can see in the corner, by Roy Bishop. This is also from the current edition of the handbook. And what we have here is the sun in the middle. This is the orbit of the Earth, and the months are put in place. So here's October, November, December, January, and so on. Out here we have the zodiac constellations along the orbit of Mars. So this is Mars's orbit, and there are 13 constellations in the zodiac. There's one called Ophiuchus most people have never heard of, but it is there, and you're just going to have to get used to it. So there's 13 zodiac constellations. And you can notice, first of all, that if you look at the orbit of the Earth's orbit is almost circular. if you look at the orbit of Mars, you can see that Mars's orbit is not circular. It's quite elliptical compared to the orbit of the Earth. So you would think, and if you take a look at the oppositions of Mars, here's one here. This is where it was in 2018. And I think I can just pop up and let somebody else come in. Okay, I'm actually getting used to this. I've never had to do this before. So here we have where Mars was. So in 2018, the opposition of Mars occurred at the end of July. And then it took 2 years plus about 2 months to come around to here, 2020. And then in 2022, it's going to be 2 years plus 2 months. It's going to be in December. Then 2 years plus 2 months. And this time the 2 months carries us over past January into December. So it's not till 2025, 2027, 2029, 2031. So, and 2033 is over here. So these are the places where Earth and Mars get closest to each other. Now you would think, click back in here. Ideally what you want is, you would think you want to have an opposition here when Earth and Mars are as close as they can possibly get, because Mars has that really elliptical orbit. The problem with that, this is a view looking south in the summertime, which is when this would happen. Here's the eastern horizon. This is the Earth's celestial equator. It's the Earth's equator projected into the sky. I put it there because from our latitude, it's exactly 45 degrees above the horizon. So if you're facing south, it's 45 degrees up to here, and it's another 45 degrees up to zenith. This is the point directly overhead. And this yellow line is the path called the ecliptic that goes through the 13 zodiac constellations. And here's Ophiuchus, this guy over here. So if you take a look at what happens, things in the sky rise in the east and they set in the west. So they rise, sort of curve across the sky and set in the west. So if the planets are down here, they're going to rise, not get very high in the sky, and then set in the west. So they're not above the horizon all that long. And in the summertime, we tend to have a lot of haze, a lot of high humidity in the air. So you're looking through this planet near the horizon, a lot of turbulence. You don't get very clear views of it. Another reason why summer times are not possibly the best is because this is the Earth and the Moon at the actual real relative sizes to each other. And both of these planets are tipped over, causing seasons. In the case of the Earth is tipped 23.5 degrees. In the case of Mars, it's tipped over by almost the exact same amount, 25.2 degrees. So this tip on Earth gives us winter and summer in the two hemispheres, summer in the north while it's winter in the south. The same thing happens on Mars, except on Mars, the seasons are twice as long because it takes it 2 years to go around. So what we're going to do now is I'm going to pop back to this diagram. This circle that's on here, this is looking down on Mars from above, and this circle represents the ice cap on Mars. So what you're seeing here is its northern ice cap, which means it's summer in the southern hemisphere because the northern hemisphere is tipped away from the sun on Mars. And in the summertime, when Mars is really close to the sun, the extra heat causes dust storms. This is from 2001, and you can see that from the Hubble telescope, you able to see lots of detail in June. By the time September rolled around, there was really nothing there except the two ice caps. So that's another reason why having really close oppositions of Mars from our latitude is not necessarily a good thing. And about these dust storms, for those of you who may have either read the book The Martian or have seen the movie The Martian, the big windstorm that causes all the problem at the start of the movies, no. Mars does have an atmosphere, but its atmosphere is only about 1% as thick as Earth's atmosphere. So it turns out that if you're standing in a 100 kilometer per hour wind on Mars, and Mars has only 1% of Earth's atmosphere, it's the same as standing in the Earth's atmosphere with a 1 kilometer per hour wind. I don't think a 1 kilometer per hour wind has ever destroyed anything on Earth. And the author freely admits he had to do that just to get the story up and running. After that, if you either watch the movie, or I particularly encourage you to read the book, because the book has a lot of neat technical geek stuff in it that's not in the movie. That stuff is all real hard science on what you would actually have to do to survive. But no, that's not going to happen. You're not going to get giant dust storms that can sweep astronauts and spacecraft over. The biggest problem it has for the spacecraft on the surface of Mars is the dust. When it does tend to settle, it tends to generate an electrostatic charge. So I don't know if any of you have ever opened one of those big bags of little styrofoam beads, and they get that electrostatics and they stick to your arms, they stick to the outsides of the bag. So that's what the dust particles do. It tends to cover over their solar panels. So that's the only real effect you're going to have to worry about. It's not going to blow you off your feet. So you think, okay, well then clearly the obvious thing to do is to go for a time of the year when the ecliptic is up nice and high in the sky. So when it's up here like this. So now the planet's going to come up, rise in the east, it's going to go way up above the stellar equator, almost up to overhead. Really good view of it. Except for one problem. If we go back to this diagram again, that's when you're over here. So this is when the oppositions are really far away. So they're not close oppositions. You're not going to see nearly as much detail. And the other problem is, if you look at the months of the year that are involved, it gets really cold at that time of the year. So ideally what you want is you want to have some time that's halfway in between. In the spring or in the fall. And right there is the 2020 opposition and the one for next year. So this year and the one in 2022 are going to be really good. And part of that is because here's the ecliptic again. Mars is going to come up. It's on the ecliptic. It's going to get high in the sky, not as high as in the winter, but definitely not as low as it would in the summertime. So that's one of the reasons why this time of the year, it's actually quite good. Okay, so where do you go to look to see Mars? Well, Mars is actually not going to be hard to find. This is the view looking south on October the 13th or the 23rd, I think it is, the day of actual opposition. A couple of weeks on either side are really good. If you look towards the south, and most of you may have actually noticed this, you've been out looking at the nighttime sky at all over the last couple of months, Jupiter and Saturn are very close to each other, and Jupiter is still very, very bright. So looking south, you're going to see Jupiter and Saturn. This yellow line is the path where you tend to find all the planets. And if you go from Jupiter towards Saturn, look towards the east, Mars is very red and it's almost as bright as Jupiter. Now this is set for around 8 o'clock. If you wait an hour, Jupiter and Saturn move a bit more towards the west because they're going to set in the west. Mars is going to get higher in the sky. Wait another hour. This is 10 o'clock, 11 o'clock, 12 o'clock. Now you would think if you go to midnight, the sun and the earth should be opposite each other. Mars should be as high as it's going to get. It's going to be exactly due south. But no, you have to wait another hour because we're still on daylight silly time. So if you want to see Mars as high as it's going to get, you want to see it around 1 o'clock in the morning. But it will be really bright. You won't be able to miss it. And it's going to be a really, really bright reddish looking star. Now, amateur astronomers like looking at it because even with a small telescope, you can actually see a lot of detail in it. This is the first telescope that I ever got. I still have it. It still works like a charm. You can see things like this in department stores nowadays, except this one, the tube and the mounting are made out of metal, not plastic like they are now. The lenses are made out of glass, not plastic like they are now. The legs are made out of hardwood, not plastic like they are now. So this is a fairly good one. It's a very small telescope. It only has a 60mm eyepiece or objective lens on it. But even with this, I can actually make some. This is a sketch I did back in 1988. There's Mars's polar cap. That's white, and you can see some lighter and darker areas on it. And one of the problems with trying to actually see Mars is that because of this turbulence in the atmosphere, you basically look and look and look and look, and every now and then the air will get steady and Mars will just sort of snap right into focus, and then you sketch as much as you can before it gets blurry again. This is a fellow in Halifax, Michael Gatto. This is his sketch of Mars that he took this year, this September, and he was up at 4:30 in the morning. the air's a lot more stable at that time of the day. And again, you can see that he was able to capture the ice caps at both ends of it. It's small up here because this is the southern one. Remember, this is, in most telescopes have used upside down. So this is south and this is north. The northern ice cap is quite large. The southern hemisphere, the south cap is quite small. Now, as telescopes got better, people started waiting for oppositions of Mars. And the first guy who really took it seriously and was really good at it was an Italian astronomer named Giovanni Schiaparelli. And this is one of his sketches of Mars from a really good opposition. And I think we have somebody else maybe popped in. No, so okay. 2 chat questions. Okay. So this is one of his sketches, and you'll notice that he sketched these sort of linear features down here. And when he published his diagram, he was Italian, so he used the Italian word canali to describe them. Now, canali in Italian can be translated into English as either channels or canals. Channels are natural, canals aren't. So you can guess which one they used. And other astronomers, back in here again, Percival Lowell, who really, he made a fortune doing something. He moved to Arizona, built an observatory, built a huge telescope, a lot bigger than the little one that I have, and he saw canals everywhere. And this is one of his maps of Mars, showing canals all over the place. And astronomers also noticed, about now they had bigger telescopes, that over the course of the seasons on Mars, the colors seemed to change somewhat. So that when it got to be summer in the southern hemisphere, the colors got a little bit maybe greener, and of course the ice caps got smaller. And people thought, well, they're usually using these, they're taking the melting water from these things and they're using them for irrigating because it looks like it's a dry place up there. And this is one of the main reasons why, for example, Lowell was fixated with this idea that there were actually these lines all over the planet because there were Martians there, they were building canals. The problem with Lowell is that most other people didn't see what he was seeing. So this is Lowell, one of Lowell's drawings from 1894. This is E.E. Barnard, probably one of the best observational astronomers of the time. This is his map in 1894. In fact, by going back to knowing exactly when he made this sketch, we now know that those 2 things he put there are in fact these 2 volcanoes on the surface of Mars. This is Antoniani, another Italian astronomer. They saw some linear features, but the human brain tends to be really weird about that sort of stuff. It'll try and put patterns where there are no patterns there. But people were convinced, especially because Lowell kept pumping the idea that there were canals on Mars, that another guy decided that he was going to get in on the action. Herbert George Wells decided he was going to write probably the first best-selling science fiction story based on this idea called The War of the Worlds, where the Martians are in fact running out of food, they're running out of water, so they decide to come to Earth and take over the place. And they had these giant tripods, they had this invisible heat ray, which I suppose nowadays we would call it a phaser from Star Trek, but it was an invisible heat ray that destroyed everything that touched it. And in the end, humans had absolutely no defenses whatsoever against the overwhelming force and technology of the Martians. If you haven't read the book or don't know how it ends, I'm not going to tell you. All I will say is that we do manage to extricate ourselves from this, but not by anything that we actually did. Great book, though. But people still thought that there actually could be life on Mars. And in fact, Orson Welles, no relation to H.G. Wells, at least I don't think there is, did a radio play version of War of the Worlds in a very jittery America in early World War II. And did it, broke in, when most people in those days were actually listening to the radio, this is the first time, when there were sort of the commercials, you'd go around to the various stations, see if there's something better on. He did the introduction as a news flash during one of these people going around. And the first thing that should have gave people a clue that it was a hoax was the Martians landed in New Jersey. I mean, seriously, who in the right mind goes to New Jersey? I would have thought even the Martians would know, you just don't want to go there. So it wasn't until the 1960s that the Americans launched a spacecraft called Mariner 4. It was basically an antenna to talk to Earth, a TV camera, and solar cells to make electricity, and it sent back images of Mars. This is one of the better ones, and it looked like the moon. No canals, no obvious sign of an atmosphere, definitely no signs of bodies of water on it. And that sort of put the end of the idea that there might actually be water on the surface of Mars, or Martians doing anything on the surface of Mars. And spacecraft got bigger and better. So in 1976, the Americans sent 2 spacecraft with miniature laboratories inside them to look for life, called Viking 1 and Viking 2. This is the Viking orbiter. So this part actually goes into orbit around the planet. And then inside this clamshell is the actual lander. And the first lander landed in 1976. This is what it looked like. It had a little arm to grab stuff. And it was quite small. It had 3 biology experiments inside it to try and look for life. And in retrospect, the answers, is there life on Mars, from the 3 different experiments was, oh yeah, no way, and not really sure. So pretty indecisive. But the miniaturization in here was incredible. One biologist said it's sort of like taking 10 meters of a biology lab counter space and cramming it into something the size of what we would now say is a microwave oven. Now, these early probes got down to the surface fairly easily. They had a big parachute that would slow them down. Mars has an atmosphere, but it's very thin, so you need a really big parachute. And I think maybe let somebody else in. Okay. So they have a big parachute, and then the parachute would disconnect when the spacecraft got fairly close to the ground, and would have little rockets that would lower it down the rest of the way. And that was how things were done. The problem was, as time went on, spacecraft got bigger and heavier to the point where you couldn't use just parachutes anymore. So this is the example of what was used to land the Pathfinder Sojourner spacecraft. And people over here looking at what the hell are they doing? The idea was you start with a parachute, then you deploy all these airbags around the spacecraft. The thing breaks off and it literally bounces and rolls across the surface. So these things absorb the energy of the impact. And what these guys are out trying to do is they were looking to see, is it possible that no matter which way this thing is oriented, you can deflate these things in the right order to then leave the spacecraft exposed? And the answer was yes, it was. And this is what happened. Pathfinder stayed where it was, and the Sojourner robotic rover separated, drove down, and went off taking pictures of its own. This is its solar panel. This is its antenna to talk back, and it's got little wheels, and it moved around. Even more probes. They get even bigger. This is Curiosity. This is the last big rover that was sent up. This is the size of a small car. Even airbags aren't going to work with this. So they came up with an idea that even the people that came up with said, this is crazy, but it might just work. So big parachutes. This thing starts off right underneath the sky crane. You separate it. This thing is still coming down at about 100 meters per second. That's like going from the top of Blondin to the bottom in 1 second. Once it gets down near the surface, it fires rockets, and it sort of hovers, and then it lowers this down on cables. These wheels deploy, and when all 6 wheels say we're on the ground, it cuts these things off, and then it flies off and crashes. So the technology just to get probes there is harder and harder. And the other reason why you can't just use bigger and bigger parachutes is because you have to separate the parachute, because if you don't separate the parachute, your spacecraft is going to land on the surface, and then what's going to happen is the parachute's going to come down and land on top of it, which means you're not going to get a chance to see anything. And here's Curiosity. This is a selfie taken from the surface of Mars by an actual still working rover. And in fact, one of the neat things about what we've been doing is Mars is currently the only planet in the solar system that is entirely populated by robots. There's about 5 or 6 of them up there still working and still wandering around. So we've been able to get lots of pictures of Mars. We've sent orbiters in space to stay in orbit around to take photographs. We can see why Mars looks red in the sky. It actually is covered with reddish dust and reddish soil and a lot of reddish rock that has a lot of iron in it. The atmosphere is very thin, but it still does have some weather. It has some clouds. And again, you can see it has ice caps up here at the top and another ice cap down here at the other pole. And by looking at the data that comes back from the orbiters, we can do all sorts of things. This, for example, is a geological map of Nova Scotia. You can buy one. It's the same size as the folded highway map, and all the different colors tell you what type of rock you're looking at, whether it's siltstone, sandstone, gypsum, how old it is, and so on. We've been able to do the same sort of thing with Mars. There's a geological map of Mars. So we're able to get really good data on what the surface is made of. We can also produce a three-dimensional model of what it looks like in 3D. So we can actually produce a really detailed elevation model. I don't know why that thing is popping down again, but it did, so I'll make it go away. So this is a contour map of Mars. There's still some things about Mars we just completely do not understand. So what they've done here is they've shaded them from blue to green to yellow to red to white. So white is highest, blue is lowest, and this is sea level. Now, sea level seems like a rather odd term to use because there's no water on the surface of Mars. What they've simply done is they've averaged, if you imagine that Mars is a sphere, and you take the average distance of all the points on Mars out from the center, it works out to be this yellow. So this yellow area here is the average distance out from the center. Deep blue is much, much lower. This is a giant impact crater basin. We don't know why the entire northern hemisphere has almost no details on it. Generally in astronomy, the more craters you see, the older the surface is. Something has completely reworked the entire northern polar region of Mars. Process is not understood. There's a huge canyon system here. I'll show you that in just a bit. And there's some huge volcanoes over here as well. So this red area is called the Tharsis Rise or the Tharsis Bulge. And it's got 4 volcanoes, the largest one, which is this one. So we can get all sorts of data about Mars from that point of view. Now this is the Valles Marineris, as it's called, the Mariner Valley. It was named in honor of the first Mariner spacecraft that took photographs of it. And this is a giant canyon system on the surface of Mars. And keep in mind that Mars is a lot smaller than the Earth. So if you compare, for example, the Mariner Valley with Earth, here's 3 of those volcanoes. You see that this canyon system runs sort of from one side of North America to the other, at least from California across to the Carolinas. It's absolutely an enormous canyon system. Give you an idea just how big it is. Here's an actual real photograph of it, or a montage of photographs of it. And this little squiggly thing coming down here, that is the Grand Canyon in Arizona. Doesn't even make a half-decent side canyon off of the Mariner Valley. So it's got real extremes of geography compared to the Earth. If you take a look at the volcanoes, this is a 3D representation of Olympus Mons, or Mount Olympus as it's called. Definitely the largest volcano in the solar system, no matter how you want to measure it. Again, give you an idea, here's again, this is from an American set of illustrations, but there's 3 of the volcanoes, and this one here is Olympus Mons. Now, one of the things to keep in mind about Olympus Mons is that in the case of Earth, we have plate tectonics, so that a lot of volcanoes that even tend to form in one place, like tend not to get very big because the crust keeps carrying the volcanoes away. That doesn't seem to have happened on Mars. It seems that when this volcano started, it just kept putting out more and more lava and getting higher and higher and higher. Now I'm going to show you, just to show you just how big this thing is. I mean, you could peel it off of Mars and it would cover all 3 maritime provinces quite easily, but it's also incredibly tall. And that's partly because all the lava came out in one place, but Mars also has a very low surface gravity. So it's easy to pile stuff higher and higher and higher because the surface gravity is quite low. And I'm going to show it to you how it compares with the tallest mountain on Earth. Now, I'm going to give you 10 seconds to think about this. What is the tallest mountain on Earth? And that's measured from the base of the mountain up to the top of the mountain. And I'll give you a hint, it's not Mount Everest. In fact, it's measured from the bottom to the top. Mount Everest doesn't even come close. I'll give you a few seconds to think about that. And here's the answer. Mauna Loa in Hawaii. If you empty the Pacific Ocean, Mauna Loa is a shield volcano, just like Olympus Mons is on Mars. It's 9 kilometers from the flat basin of the Pacific Ocean up to the top of Mauna Loa. In the case of Mars, it's 27 kilometers up to the top. Now, what they've done here is they've exaggerated the vertical scale in this by a factor of 5, just to sort of really show what's happening. And in the case of Earth, the reason why you have a whole chain of volcanoes here is because this part of the Earth is moving, and the magma that flows out, flows up, makes a volcano, and then that volcano gets carried away. And then another one starts. And that's why if you look at the Hawaiian Islands, there are a series of old volcanoes. The further to the west you go, the older they are and the more eroded they are. They get smaller, 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 and then they still continue underneath the Pacific Ocean where you can't see them. So very extremes of geography on Mount Olympus. As mentioned, it does have an atmosphere, and it actually does have some weather. It does have some clouds forming in it. Its atmosphere, though, is mostly carbon dioxide. So in that way, it's like Venus. Venus's atmosphere is almost all carbon dioxide. Mars's atmosphere is almost all carbon dioxide, even though it's very, very thin. Earth is sort of the oddball out, having an oxygen-nitrogen atmosphere. But it turns out if you take all of the carbon dioxide that's sequestered in the Earth, either by being dissolved in the ocean or stored in fossil fuels or stored in carbonate rocks like limestone, if you take all that carbon out and put it back into the Earth's atmosphere, our atmosphere would be about 100 times thicker and made up almost entirely of carbon dioxide, just like Venus. So all 3 planets have atmospheres made up almost entirely of carbon dioxide. Earth has put all that carbon dioxide and stored it in various places so that other gases tend to dominate it. There's weather there. Besides the dust storms, there's dust devils, little mini tornadoes that travel around. You see streaks left by them in the dust on the surface. And there's water on Mars. Now, even though there's no liquid water, there's a bunch of reasons why we know there's actually water on Mars. And this is mostly from looking at the images coming back from the orbiters that actually go around and around Mars, taking photographs over and over and over again. Here we have an impact crater. The heat generated by that impact melted frozen water under the surface, turned it into mud. The mud flowed away from the site of the impact and then froze again. And we see numerous places on Mars where this actually happens. We also see these types of features where you have a crater with what clearly shows a teardrop island caused by water flowing around it. The only place you ever see this type of feature on Earth is when you have an obstruction in the middle of a river, like the Mississippi or the Nile or the Amazon. Any of the big rivers carry a lot of sediment. As the water flows around, it slows down in behind and it drops the sediment off. And again, here you see another impact crater with that frozen mud around it. There's places on Mars where the rock on the surface has been carved out by running water. All these channels coming down and cutting through this rock here and coming out down at the bottom. So there's lots and lots of evidence that Mars had liquid water on its surface in the past as well. This is another channel here caused by running water. And I'll just show you a zoom in view of what's in that orange part of it. And again, on Earth, you see that feature only caused by running water. Here's evidence for a lake on the surface of Mars. So here we have inflow channels where the rain has flowed across the rock, cut channels in it. This is the shoreline running along here. And in fact, you can see over here, the shoreline continues. You can see the change in color caused by the fact that the chemistry of the rock has been changed because water was here. And in fact, we found lots of geological minerals that on Earth only form in the presence of liquid water. We found those minerals on the surface of Mars as well. And then here's where the channel flowed out. So how much actual water is there? Well, the polar caps, this is a view of one of the polar caps in late spring. This is late spring on Mars. You see the cap is quite large and it's quite small over here. Because of the very, very cold temperature and low pressure, the permanent ice caps on Mars tend to be made up of water ice. The one that gets bigger and smaller as the seasons change tends to be made up of carbon dioxide, or dry ice as we call it on Earth. And we call it dry ice because at the temperature and pressure on the Earth's surface, if you take out a big chunk of frozen carbon dioxide, it doesn't melt like a piece of ice does and then turn into a gas. It goes from being a big block, and it just gradually gets smaller and smaller and smaller as the carbon dioxide turns from a solid directly into a vapor. Now that happens on Earth when the conditions are right with liquid water. There are conditions on Earth where you can have the right combination of temperature and atmospheric pressure and humidity, and that's where frost comes from. So frost is the reverse process. Frost is where you have water turning from a gas directly into a solid on the surface of something on Earth. So we're familiar with it. But when the polar caps get to their largest extent, about a third of the atmosphere of Mars is tied up in ice at its pole. So it has the most atmosphere in between summer and winter. So in the late spring and the late fall. And we have even more evidence that there's water. This is the lander that I had showed you the last time. This is Curiosity. This is one place where it was scraping around in the dirt, and they are quite sure that this white stuff that's been exposed is water ice, frozen under the surface of Mars. So in the distant past, Mars may have had a lot more water on it. It definitely would have had a much thicker atmosphere, which meant it was able to keep liquid water. And here we see maybe the Mariner Valley was there and it was sort of filled up with liquid water at that time. But unfortunately for Mars, it's just small enough that it can't really hold on to any gases for very long times. So the ice that ended up underground froze there, and as Mars gradually lost its atmosphere, it lost one of the key gases that acts as a greenhouse gas, which is water. That's why it's always nice and mild in the winter when it's overcast at night. The water vapor acts like carbon dioxide does. It traps in the heat. And as Mars's atmosphere got thinner and thinner and thinner, it gradually got colder and colder and colder and colder until the only water that seems to be left is bits in the poles and what's frozen in the ground. Okay, and I think I will stop there, and I'll go back and see if anybody has any questions. I have to quit out of there.
I had a question. You mentioned the optimal date in October?
Yes, it's October, I think it's the 23rd.
Thank you.
Okay. You think I would know that off the top of my head, but I have it on one of the slides back here.
Maybe you can remind us.
Yes, well, like I said, you can see it gets really big right around then. So, you know, a couple of weeks on either side will be fine. And what will happen after opposition is Jupiter and Saturn had opposition back in July. They're still hanging around in the evening sky. So what happens is Mars will slowly move towards the sun in the evening sky. So you'll get to see Mars all throughout the fall. It's not going anywhere. It's just it's going to be at its brightest in mid-October.
Thank you.
I had a question about, are the rocks found on Mars the same kind on Earth? Actually, yes, they're very similar in a lot of cases. In fact, one of the ones that they found, they've nicknamed them blueberries because they look like big blueberries, and they're one of these minerals that we have the exact same mineral on Earth. It also forms little round spheres on Earth, but on Earth it only forms in areas of liquid water. But the main reason why Mars tends to look red is it has a lot of iron in the rocks at the surface. The surface, it's literally rusted, which is why it's reddish colored. And the changing seasons that they thought they saw in the late 1800s, early 1900s, is basically there are seasonal winds, just like there's seasonal winds on the Earth. And it tends to move the dust around a bit, slightly covering or uncovering the underlying rocks, which changes the color slightly. So when people thought that the areas were getting greener, they were just getting a bit darker, but they thought, well, on Earth that happens when the plants start to grow, but that's not the case on Mars. We know it's just dust being moved around by the breeze up there. Any other questions?
They've just they feel that they've just discovered evidence of possible life of some kind on Venus. Um, depending on how you define life, is there evidence that there ever was life in any form whatsoever on Mars? And if so, was it all in the past, or did they think that there are some kind of maybe I don't know, viruses or bits of nucleic acid or something anywhere on Mars now?
Well, what they were looking for in the case of the Viking spacecraft, the 3 experiments, one was to take some soil, put it into a liquid with what they thought would be food, and see if, I think it was either oxygen or carbon dioxide was released. Another was to look for various isotopes of carbon, and I can't remember what the third one was. One of them said, oh wow, there's lots of life here. The one looking for carbon in the soil, because when dead things die, the carbon stays there, said, no, there's no carbon here whatsoever. And the third one was really ambiguous. And they think now that the one positive was caused by some weird type of chemistry in the clays. But they've gone back and tried to actually reproduce that using all sorts of different types of minerals, and they just can't reproduce it. So they still aren't quite sure. Most of the modern spacecraft that are roving around are there more for geology, and they don't have biology experiments on them like the original Vikings did. Now, that being said, there is an actual space mission that is actually funded, and it's going to go on its way. I can't remember when it's being launched. It may actually be already on its way. There were 3 spacecraft that were launched just this summer towards Mars. It turns out that that's when Earth and Mars get into opposition, you can send a spacecraft from Earth to Mars using the least possible amount of fuel. I think China sent one, I think the States sent one, and I think United Arab Emirates sent one. But one of the landers that the Americans are going to be sending is going to be going around, picking up little samples and sealing them into test tubes and just dropping them behind it as it goes along. Then they're going to send another spacecraft that is actually going to put a lander that's then going to go around and pick them up and bring them back to the lander and put them into orbit around Mars. And then the spacecraft in orbit around Mars is going to grab this other one with all the samples on board it and leave Mars and come back to Earth. And actually bring actual real samples of drilled cores from the surface of Mars and bring them back to Earth so we can actually examine them here. And I can bet you they're going to quarantine the hell out of them a lot more than they are for COVID-19 before they actually try to do anything with them. They'll probably be inside some sort of quadruple redundancy, because if there is some sort of life in there, we have no idea what it might be like. But Venus, it turns out that the gas that they found on Venus is one of these things that it's like oxygen. The only way you can actually have it there stably is to have something making it. And the only thing we know that makes it in those quantities is life processes. Oddly enough, in particular, the guts of penguins release phosphine gas on Earth. But bacteria do it as well. So there's bacteria on Earth that do it, and there's also gut bacteria in penguins that release phosphine gas. So the thought on Venus is that maybe there's some sort of bacteria high floating in the cloud layers. And even on Earth, once you get up above as far as an airplane can go, there's a whole area from about 20 kilometers up to about 120 kilometers where we simply can't get there. The atmosphere it's too thick to put a spacecraft in orbit, it would decay, and it's too high to get there in an airplane. So and even when they go up as far as they can with planes, if you take samples of air, there's bacteria and stuff living in the air, even at that elevation on Earth. So anyways, it's going to be curious to see what they actually end up finding. Question, how old is Mars? It's from XAEA12, Elon Musk's daughter, apparently. Mars is about the same age as the Earth. It would have been formed at the same time that the Earth did, so about 4.6 billion years ago. So it would have formed in the inner part of the solar system. and probably didn't get as big as it could have because of the influence of Jupiter, which probably got rid of a lot of the smaller pieces from which the inner planets accumulated. But Mars has basically been doing the same thing the Earth has been doing, just sort of circling around the sun, except in the case of Mars, it's just been slowly and slowly losing its atmosphere and getting colder and colder and colder. Oh, another question, how does the iron rust? Does it need oxygen? Well, there's lots of oxygen in carbon dioxide. So in the case of Mars, Mars does not have an ozone layer. So with no ozone layer, ultraviolet light from the sun can take oxygen out of CO2 and it can rip the oxygen atoms off. And oxygen is it's a deadly, deadly gas. It took life on Earth a long time to adapt to it because it combines chemically with anything it can get its hands on. If you want to see just how deadly oxygen is, if you look on the periodic table, the gas that acts like oxygen even worse, and it's right next to on the periodic table, is chlorine. Nobody would go around breathing chlorine gas if they could help it. But when life first arose on Earth, that's what oxygen did to it. It's highly reactive. In fact, I often tell students, I ask them, does aluminum rust? And they'll say, no, it doesn't rust. You take a piece of aluminum and you cut it with a hacksaw and it never rusts. In fact, it rusts instantly with oxygen. The big difference is iron oxide, as in the body of your car, iron oxide will let water and oxygen pass through it to get at the iron in behind it. Aluminum oxide is impervious to both oxygen and water. So that's why aluminum is such a good thing to make, say, things like chalkboard railings out of. It's nice and light, and it does rust, but it rusts instantly. So oxygen is a really highly reactive gas, and if it gets its hands on anything, including anything that has iron in it, it forms rust very quickly. The speeds of the planets in their orbits, that's just Newton's laws. So Newton's laws of motion and his law of universal gravitation, all that stuff just falls right out of it. So if you've ever learned Kepler's laws, Kepler's 3 laws of planetary motion, one is that the planets orbit in an ellipse with the sun at one focus. The second one is it speeds up and slows down so that if you connect the sun and a planet, the line that it sweeps out through space sweeps out equal areas of its orbit in equal times. And his third law that says how long it takes to go around depends on how big the orbit is. Those 3 laws he came across by looking and seeing what the planets did, but he couldn't explain why they did it. Newton came up with 3 laws of motion and a law of universal gravity, and Kepler's laws just fall out automatically out of that. So it's Newton's law of gravity and Newton's laws of motion that explain why the planets do what they do. And I do believe there are sedimentary rocks on Mars as well, which is one of the reasons why they're also quite sure that there's actually was water on the surface of Mars in the distant past. One of the big problems with these rovers is you can't move them very quickly because there's quite a time lag between the time it takes a signal to get from Earth to Mars. So even when Mars is really, really close to us, that delay is still about 4 minutes one way. So if you can't drive those rovers in real time, because in real time, if it sends you back a picture that the rover is about to go over a cliff, it takes 4 minutes for that picture to get back to you. And that's assuming that you're not on the far side of the orbit, in which case it's going to be more like 16 minutes. So if Earth and Mars are on the opposite sides of their orbits, it sends a picture that there's a cliff right ahead. 16 minutes later, you get the picture, you say stop. 60 minutes later, the signal gets the spacecraft to say stop, at which point it's already fallen off the cliff. So they take a whole bunch of pictures and they only move it in very small amounts, just because they don't want to actually lose it by some means like that. Somebody else has asked about why did it lose its atmosphere? If you take something on Earth and toss it up, there's a thing called escape velocity. In the case of Earth, if you take something at the Earth's surface and if you can get it going 11 kilometers per second straight up, gravity can't hang on to it. It will not come back. Now, the smaller the planet is, the lower that number is.
Questions now.
And the gas particles in the atmosphere move along pretty quickly. I think I worked it out one time. I think the oxygen atoms or oxygen molecules that are in the air right now are moving along at something on the order of half a kilometer per second. So all the oxygen atoms around you are traveling about 500 meters per second. So what that means is that over enough time, some of those will be moving faster, some will be moving slower, and if they get moving fast enough, the planet can't hold on to them and they just escape to space. So for example, on Earth, hydrogen gas and helium gas move really fast. And if you release hydrogen or helium gas, they simply float to the top of the Earth's atmosphere, heat up, and just leave. Which is one reason why a lot of people are worried about the helium supply, because you can't make helium. Once you're out of helium, you're out of helium. You can't, it comes up out of places like natural gas and oil well deposits. It's a byproduct of radioactive decay, but once the helium on the Earth is gone, we can't make it anymore. Well, we can make it in very small amounts with hydrogen bombs, but that's not a technology you want to use just to be able to make helium balloons. In the case of Mars, because Mars is so much smaller than the Earth, its surface gravity is so much smaller that its surface gravity just isn't strong enough over long periods of time to hang on to all those gas atoms, and that's why they just slowly left away in space. Will our planet eventually become like Mars, and if so, how long would that be? Actually, if Earth is going to become like anything, it's going to become more like Venus, because the sun is very slowly but very surely, this is way outside the realm of climate change. This is going to happen whether we get climate change solved or not. The sun, over the last 4.5 billion years or so, has been very slowly but surely getting bigger and hotter, which is a process because as it uses fuel, that's just what it does. And it's going to keep getting bigger and hotter. So the sun is going to give us more and more and more energy, and it's eventually going to heat up the Earth's surface to the point where it's going to start heating up the oceans and forcing the carbon dioxide out into the atmosphere. And of course, carbon dioxide is a greenhouse gas. If you put more carbon dioxide into the Earth's atmosphere, you raise the temperature, which is going to increase the temperature of the oceans even more, which is going to force even more carbon dioxide out of the atmosphere. And you just get a runaway effect like that. If you get it hot enough, the carbonate rocks like limestone break down and start giving off carbon dioxide. So long, long before the sun burns out, the Earth is going to be more like Venus. And then just to make matters even better, in about 3.5 to 4 million years, the sun's going to go through what's called a red giant phase. It's going to swell up, it's going to engulf Mercury, it's going to engulf Venus, and it may or may not engulf the Earth. At that point, the Earth will have no atmosphere. It'll be so hot that even the Earth can't hang on to its atmosphere. The sun will be losing mass, so the Earth will be slowly backing away from it. So the question is, will the Earth be able to back away faster than the sun comes out to meet it? But by then, there's going to be no life on Earth whatsoever. But that's not for billions of years, so I wouldn't be too worried about it.